Okay, so are we ready for class? Okay. So do you remember what we did last time? Do we have our answer for the peddler man question? Do you want to take it out? Don't tell me. Look at his face again. Will you trust him with all of the money you have? You have one chance to figure that answer out. Don't tell me.
Are we going to tell you by the end?
Yeah, you will. Well, oh, trust me, you will tell me whether you want to or not.
I think you know my answer.
Okay, but don't tell me yet, because we haven't done all the math that goes behind it. So we will figure that out. Okay, do we have an answer?
Yeah.
Okay, so what was the property we developed last class? What was it called? Entropy. And this is the magic box he's trying to sell us, yes? And what was so fascinating about this magic box? It will give you unlimited hot and cold as long as you have access to compressed air, correct? Okay. And what is the one thing we developed that I never, ever do? I taught you something new for once that did not depend on manipulation of previously known facts. Yes? And that property was called entropy. Well, it was manipulation, but in a slightly smaller sense, right? We did develop the extropy, but then we developed entropy. Anyone remember the formula for entropy? Good morning.
Morning. S is equal to or less than 0.
Yay! Good job.
Or
Woohoo!
greater than.
Greater or equal to 0. It will always be positive. But does anyone remember the actual definition?
Delta S equals MC.
No, not the other one. Q over T. That one. So what was the formula for entropy?
Oh, delta S equals the derivative of T from T final to T initial Q of T.
Excellent. So what was delta S? Q over T, or integral of 1 over T dq from some initial to some final. And that first time we called that property, it's new, completely new, and we called it entropy. Okay, and I also said, how much do we know about entropy? Pretty much. We know as much about entropy as we know about energy.
I think you said less.
Oh yeah, actually, as much. But in fact, we know even less than we know about energy. What do we know about energy? It's conserved. Done. What do we know about entropy? It's partially conserved. Good job, right? It's only conserved in the forward direction. So if you scramble an egg, can you unscramble it and make it into a whole egg again? So entropy only works one way, right? We talked about that last time. Okay, so we also said entropy can be defined for 2 different scenarios. For macroscopic and microscopic situations. What is the macroscopic definition? It involves heat transfers, and it involves temperatures at which these heat transfers happen, which is why it is defined as delta S equal Q over T. And we'll talk more about this in a second. And then we said that there was a microscopic definition of entropy that involves counting the ways in which atoms and molecules can be arranged in a system. And what is a system, guys? Anything under consideration, right? Okay. Now going back to Zan's explanation for entropy, what did you say? Delta S can only be?
Greater than or equal to 0.
Good. What do we call that? We call that formally the entropy principle. Entropy principle states what? Delta S could either be equal to or greater than 0. Can never, ever, ever be less than 0. So which leads us into the second law of thermodynamics, which now we are going to write out. Ready for it? Second law of thermodynamics, which states when changes occur in a closed system, what's a closed system? But what can change? What can be exchanged? Excellent. Its entropy either increases for irreversible processes or remains the same for reversible processes. But it never decreases. I want you to put this in a box and remember that forever. Okay, then we also talked about one other very important thing, which was quality versus quantity. And we said very specifically what does our first law deal with? The quality of energy or the quantity of energy? Quantity, yes? What was our first law? What's the definition of our first law? Delta U equals Q plus W. What happens to delta U? What is delta U? Energy? If you do work on the system, what happens to delta U? First of all, what is that called? Compression. What happens to delta U on the left-hand side of this equation if I do work on the system? Right? What happens if the work is done by the system? What is that called? And what happens to your delta U? Goes down. So energy can be converted from one form to another, right? So the first law only deals with the quantity of energy, right? Whereas the second law, I want you to write the first law here. So then why do we need the second law? Because we also have to worry about the quality of energy in your system, right? So imagine you built a dam, a hydropower dam on a hill. On the other hand, somebody else built it on a really high mountain. Which has better quality of energy? Well, somebody else. Well, not mine, because mine is on a small, sloopy hill, right? So I won't get too much energy out of that system. But somebody else is dropping potential from, okay, I'll give you an example. I have this ball and I need to drop it. Who's the tallest person here? There you go. Come on here. Everyone turn around immediately. So we are going to drop this ball from my eye level, and he's going to drop it from his eye level. Our eye level, which will have a better quality downhill. Why is nobody pointing at me? Me, thank you. Right? Does that make sense? We both have energy, potential energy. Which one of us has better quality potential energy? Whose velocity will be more when it hits the ground? Oh my God, no one's pointing to me. That's sad. Okay, we'll test it. Okay, I'm gonna drop it from my eye level. See how high it bounces. Wait, how do we do that? See how high it bounces. Now you do the same. From eye level, drop it. Yeah. Which one had better quality? Thank you. You get an A. Right? Does that make sense? So the second law additionally deals with the quality of energy that you had to begin with. So imagine he needs less force to get equivalent output. I will need to actually put force in to get the equivalent. Does that make sense? So that is why we needed the second law. Good? So how do I write this? How do I write all of that?
Draw it.
I'll draw it. Like draw Andy? I can try. So this is me. This is Andy.
You know how like water boils faster than regulations.
Low quality. Low quality. High quality. And this is why we need the second law.
You never do that in textbook.
You're in the textbook now. Really tall, skinny Andy.
So I'm just going to be the really tall kid in the class for the next revision.
For the next edition, yes, you will be the really tall person in the textbook.
Make sure to have his name in there.
And yes, I will remember his name. Andy, do you want to be called Andy or William? Cool. That is actually a good example. It's so totally going in the next edition.